Mastering artificial neural networks. Your neurons are secretly running your life. Neurons that process and transmit information? The mysteries of the human brain have long fascinated me. As I delved into the world of artificial neural networks, I couldn't help but think of my own experiences with negotiation. It's fascinating how these networks mirror the way we think, make decisions, and adapt to new information. I recall a particularly challenging negotiation I was involved in, where I had to navigate a complex web of interests, priorities, and constraints. It was like trying to optimize a neural network, where every node or neuron had its own set of weights and biases that needed to be adjusted just so. One misstep, and the entire system would collapse. As I worked through the negotiation, I realized that each party had its own unique activation function. Some were more sensitive to perceived threats, while others were more receptive to creative solutions. I had to adjust my approach, much like adjusting the learning rate of a neural network, to find the optimal balance between assertiveness and empathy. But it wasn't just about finding the right balance. I had to continually update my understanding of the situation, incorporating new information, and adapting my strategy on the fly. It was like training a neural network on a new data set. The more data I gathered, the more accurate my predictions became. As the negotiation progressed, I began to notice patterns and relationships that I wouldn't have seen otherwise. It was as if my brain was creating its own neural network, connecting the dots between seemingly unrelated pieces of information. This newfound insight allowed me to identify creative solutions that satisfied all parties involved. However, as I navigated the complexities of the negotiation, I couldn't shake off the feeling that I was walking a fine line between conviction and compromise. It was like the neural network was whispering to me, "Be careful, don't overfit the data." I had to stay true to my core values while remaining open to alternative perspectives. In the end, the negotiation was a success, but it left me with a deeper appreciation for the intricate dance between human connections and the artificial neural networks that mimic them. As I looked back on the experience, I realized that the principles guiding these networks, adaptation, iteration, and contextual understanding, were the same principles that guided effective negotiation. In the world of artificial neural networks, a single neuron is just a small part of a larger system. But when combined with other neurons, it can create something truly remarkable. Similarly, in the world of negotiation, a single conversation is just one thread in a complex tapestry. But when woven together with empathy, creativity, and a willingness to adapt, it can create something truly remarkable, a solution that satisfies all parties involved. As I reflect on my experience, I'm reminded that the pursuit of knowledge is a lifelong journey. The more I learn about artificial neural networks, the artificial neuron, also referred to as a processing unit, is an essential element of an artificial neural network. Each artificial neuron receives one or more inputs, which are values from the outside world, or outputs from other neurons. These inputs are multiplied by a set of learned weights, which determine the strength of the connection between the input and the neuron. The weighted inputs are then summed, and the result is passed through an activation function, which determines the output of the neuron. There are several types of activation functions, each with its own characteristics and uses. The sigmoid function is one of the most common activation functions. It maps the input to a value between 0 and 1, which is useful for binary classification problems. Another common activation function is the rectified linear unit, ReLU, which is computationally efficient and easy to compute. The ReLU function maps all negative values to 0, and all positive values to the same value. Once the output of the neuron is computed, it is sent to other neurons or to the outside world. The output of one neuron can become the input to another neuron, allowing the neural network to learn complex patterns and relationships in the data. The processing units in an artificial neural network are organized into layers. Each layer consists of multiple processing units that operate in parallel. The outputs of one layer become the inputs to the next layer, allowing the network to learn increasingly complex patterns. The number of layers, the number of processing units in each layer, and the connections between layers can vary greatly. depending on the specific problem being tackled. Artificial neural networks have many applications, including image recognition, natural language processing, and decision-making systems. They are particularly useful when the problem is complex and difficult to model using traditional algorithms. Training an artificial neural network involves adjusting the weights and biases of the connections between neurons to minimize the error between the predicted output and the actual output. This process is typically done using backpropagation, an algorithm that computes the gradient of the error function and adjusts the weights accordingly. In summary, artificial neurons are the fundamental components of artificial neural networks. They process and transmit information by receiving inputs, computing an output using an activation function, and sending the output to other neurons or to the outside world. The organization of these processing units into layers and the connections between them allow artificial neural networks to learn complex patterns and relationships in the data, making them a powerful tool for many applications.